All right, problem number 5 will be a conservation of energy problem, a 20-point problem. All right, maybe like this. A 5-pound collar is released from rest at A. It travels along the frictionless guide. Determine the speed of the collar when it strikes the stop B. The spring has an unstretched length of 0.5 feet. All right, so you know it is a conservation of energy problem. But if you didn't, then problems like this that have springs, that have velocities, that are asking for velocities, before and there's no collision, then they're good conservation of energy problems. So I do this, right? The potential energy plus kinetic energy plus any non-conserved work by an outside external force equals the potential plus kinetic energy final. And the potential could be both gravity and a spring. The potential energy could be both gravity and a spring. So that's kind of how I do that. And I like to go ahead and write, this is probably not necessary, but I like to go ahead and write the whole equation, even though I know a lot of things are 0 to begin with or 0 to end with. But I like to write that whole conservation energy equation to put something down on my paper. It feels good when a lot of these things are going to 0. Okay, so now a lot of times, this is starting here and ending here. Make sure you visualize where it starts and where it ends, because sometimes it draws it, kind of at the middle of where it's starting, where it's ending. So visualize it starting from A. So this spring is right here. All right, it's starting from A. Let's look at this MGH. Let's look at this MGH. Kind of like, remember the projectile, you can choose anything to be your ground. You can choose anything to be, you can choose your ground down here, choose your ground up here. Just whatever you visualize, whatever is easiest for you to visualize. I'm going to choose this down here to be my ground. That would mean it ends at a height of 0. It starts at a height of 2.5, right? It starts at a height of 2.5. So this would be, let's see, okay, sorry, and here, these are English units. Makes it a little bit more complicated. For English units, that pounds is the weight. It is a force. That's not the mass. That is M and G combined. So this is 5 times 2.5 feet. I should keep up with my units, but as long as I'm in feet, I'm good. Feet per second squared. Now, some of you might have wanted to do this. The mass right here is 5 over 32.2, then times 32.2. Right? Do you see why you could just group the mg together for the weight of 5 pounds? Okay. Now, if it's SI units, then this might be kilograms, and this would be 9.81 times height. All right, but anyway, so this is English units. So this is 5 times 2.5, and my other side is 0. All right, the spring, 1/2 K, the X. Remember, X is not the length of the spring. X is the amount of stretch or compression of the spring. But what is the length of the spring? When it is right here, the length of the spring is 2.5. Its unstretched length is 0.5. So how much is it being stretched? 2. Right? How much is it being stretched? 2. 2 feet. As long as we're in feet, pounds per feet, feet per second squared, we're good. All right. It said it started from rest, so there's no velocity. There are no external forces. That right there, what I'm looking for is a force that's either drawn on there or a force in a rope. Right? Force is drawn on there or a force in a rope. I don't have either of those, so that's it on the left-hand side. On the right-hand side, MGH is 0, right? We're down here at B. We're down here at B. The spring is right here. This green length would be the spring. So this would be 1/2 K. What is its X? Look up there. All right, so this is 1 foot. And the unstretched length is 0.5. So this is 0.5 squared. All right, plus 1/2. All right, so now here is for English units where we have to be careful because that is mass, not weight, and it's not mg together like we got away with simplifying the math right there because mg was together. This is m, so this needs to be 5 divided by 32.2. I'm not keeping up with my units, but units work out again if we're in pounds, if we're in feet per second squared. Whew, there we go. This equation should only have one unknown. You can only solve for one unknown in there because it's one equation. It's not like it's an x equation and a y equation. It's just a one magnitude equation. And I would get the velocity, 16.0 feet per second. 16.0 feet per second. So the only tricky part, well, this was a little bit tricky because it was English units, right? Be ready for SI units or English units. The only tricky thing I think sometimes is just make sure you visualize and double and triple check where it starts and where it ends, so that you can look at that spring, so that you can look at that MGH, figure those out. And then also be careful. We've done a lot of things that started from rest, but I've looked at some problems where it says, hey, it starts with a velocity of something right there at A. So be careful. Sometimes you do have this 1/2 mv squared. I don't know if we've had it very often in these problems, but sometimes you do. So first thing I do, write my conservation of energy, remind myself potential can be both gravity and spring. I like to write this whole thing, and then some things will go to zero, but just look at them individually. This almost like this is, 3 or 4 small problems. A small problem is figuring out these MGHs, initial, MGH, final. Small problem is looking at where it is initially, what is the length of the spring. All right, so what does that mean? The x, the stretch of the spring, would be. What is the velocity right here? What's MGH final? The 1/2 kx squared final, 1/2 mv squared final. You can only solve for one unknown, so hopefully you'll have one unknown in that equation. All right.